Welcome everybody to a discussion with Ceren Dag regarding many-body quantum chaos in stroboscopically-driven cold atoms. As always, you can find a link to the paper in the description, and without further ado, we're going to get started. I think a good place to start the discussion would be to just introduce quantum chaos, if you would mind giving a high-level overview of what that means and how it compares to the classical case.
Yeah, that's a very good question. Okay, so quantum chaos is actually different from it's its own concept. So it's different from classical chaos. So it really goes back to like Wigner's papers from 1950s. So okay, so based on in classical chaos, let me actually reference back to classical chaos first. Classical chaos is really defined based on the classical phase space trajectories, how they deviate from each other in time, and basically how these classical phase space trajectories are sensitive to perturbations. So that sensitivity to perturbation is captured by Lyapunov exponent in classical chaos. So when we come to quantum chaos is different in the sense that we don't have those kind of classical phase space trajectories. We also really cannot take this concept and just blindly apply to the Hilbert space and then the states in the Hilbert space. But really it was Wigner who first realized that such perturbation, so such sensitivity to perturbations can also be seen in quantum mechanics, but can be seen at the level eigenenergies and eigenstates. So what that means is at the time the problem that they're working with was hydrogen atom, and also other nuclei atoms, so other nuclei, and the Wigner was approaching the problem as, okay, there are so many energy eigen levels to these objects. Instead of trying to understand them one by one, let's look at them in as a statistical ensemble. So it's like an ensemble of energy eigen values. And based on that, he argued the random matrix theory should be a good description to understand the statistical properties of these energy eigenvalues of the say hydrogen atom nuclei.
Okay.
Yeah,
And so we're mentioning.
Okay,
Yeah,
go ahead.
sorry, go ahead.
No, I was just gonna say this is where random matrix theory comes in. It's of course a branch of mathematics, but that is there are certain distributions that the random matrix theory predicts that we should be observing as the properties of these energy eigenlevels, and according to the experiments we do actually observe these. So random matrix theory does indeed come in physics and affects the properties of these quantum mechanical objects.
Mhm. And in a nutshell, what we're using it for is to map this problem statement onto a particular distribution. So we're looking for that distribution. We don't know what it is going in, and random matrix theory helps us evaluate what that distribution would be. Is that understanding
Yes,
correct?
I think that
Okay.
that understanding is correct. Yeah, in particular, those distributions, we know what we expect from random matrix theory. So what we call, for example, the Wigner-Dyson distribution is one of them, or also goes through Gaussian ensembles. Depending on the symmetries of the system, it could be a Gaussian orthogonal ensemble or Gaussian unitary ensemble. So these are basically just what typical the distributions that we see in the random matrix theory, and comes out actually as the properties of the energy eigenlevels in some quantum mechanical systems.
Mm-hmm. Okay. I want to focus on those particular systems that we have in scope now, or not necessarily in scope of the paper, but in scope of our interest, let's say. So you mentioned, I believe, hydrogen atom as your original example. Do you have some other ones as well that would fall into the scope of where our understanding could be enhanced by this kind of investigation? What kind of systems are we looking at with random matrix theory and trying to figure out these distributions for?
So the hydrogen atom was the first example, and then there were other like nuclei that people looked at it. But I would say the one that was like most relevant now for us is that like there's this very famous paper by BGS. There are three people basically, like BGS stand for the capital of their names, the last names. That's from 1980s, and we do have like what they studied there was like quantum billiard models. These are basically like a quantum particle subject to a stadium potential or any kind of potential, but typically the stadium potential. So these are basically single particle quantum chaotic models. And what they did there, like they also look at the eigenenergy distributions, specifically the energy level distributions. Actually, the first thing that we look at is the energy level distributions, and they saw that in this particular like model that doesn't have any like direct relation to like atomic nuclei, also show like those distributions that we expect from random matrix theory. Based on this, they actually like conjecture, and today it's called BGS conjecture, that any quantum mechanical model with a semi-classical limit should actually, any quantum mechanical and chaotic model with a semi-classical limit should actually like follow random matrix theory, and these like the predictions of random matrix theory are called actually like fluctuation laws, and we say there is a universality to this fluctuation law. So there are universal fluctuation laws in the eigen spectrum of these chaotic quantum mechanical models.
Okay. Bringing that now to the models that are in scope of this paper, did you investigate that potential here as well, or did you investigate other models? Because I think you have 3 models in scope of the paper, but I'm not quite sure if one of them maps one-to-one to that particular potential.
Yeah, so that was from 1980s, like BGS conjecture with like the stadium models, and there has been a lot of progress actually since then. So now coming to like what we are doing, what we're doing is actually a part of like a community like research endeavor, let's say. People have been studying quantum many-body systems for a long time now, and not just a single particle systems basically, but like let's say like many like atom or many spin systems, and like frankly, not all of the quantum many-body systems have a semi-classical limit. Like that means like they're not necessarily connected to a classical limit. You cannot necessarily take this like quantum many-body system and write down some like classical equation motions for them. It's just like doesn't such a thing wouldn't capture completely the Hilbert space physics. Even though this is the case, today, like one of the first things that we do if we wanted to check whether the model is quantum chaotic or not, we will just go and look at the energy level spacings, or like in general the energy levels, and see what kind of distributions coming out from them. And if it's really like like RMT, random matrix theory, like predicted distributions, then we say, okay, this is a quantum chaotic model. So it literally all those ideas that I just mentioned coming from 1950s, it's been like shaping like what we are doing today for like a more, let's say, complex systems in quantum mechanics. And
so are you saying that's
go ahead.
Yeah, sorry. Yeah. Okay. Are you saying that's a bijective mapping, more or less? That if you also observe the distributions that would be predicted by random matrix theory, you can infer that the system is chaotic. So you can actually use that as a test for it as well. Okay.
Exactly. So that is actually
like, wouldn't you be able to expect that? Yeah, wouldn't you be able to expect an overlap in the distributions between like classical systems that nevertheless end up with the same distribution of of eigenstates or eigenstate energies?
So let me first say, like, this is basically most accepted diagnostic of quantum chaos today in the community. But like, if you wanted to define quantum chaos, it's still, I would say, like a research area, how we can actually define quantum chaos, because it doesn't have like a precise definition as a classical chaos has. So that's
Hmm.
let me just put this here. And then the other thing is that you were saying like whether there is some sort of connection. Can you repeat the last question again?
I believe my last question was whether you would see like why you're not able to see an overlap in the distributions between a classical system and a quantum chaotic system. If you're saying that you can use the distribution of energies or whatever distribution we're looking at for the system,
Mhm.
um, how come you're not able to observe that same distribution that we see in the quantum chaotic case from another system?
Um, so first of all, yeah, the quantum chaos is different from classical chaos.
Yeah.
Right? So and these distributions like we do actually like could be very different systems in like quantum mechanically could be very different microscopically different systems, but if they're chaotic actually they're going to show the same distribution. Like that's why it's universal basically. It's like a
Hmm.
particular distribution that we call Wigner Dyson. It's also in this paper we are showing like how it looks like. That's
Hmm.
like one diagnosis again. And
Hmm.
yeah, I don't know if this actually really answer your question because I think it was hard for me to understand what you are asking.
Maybe my question is not so well formalized. I was just surprised that you could use the outgoing distribution as a diagnostics tool to actually infer that this is a chaotic system.
Mm, yeah, so as I said, yeah, it is basically like a diagnostic for it. It's
Yeah.
not the only diagnostic. There are a few other
Hmm.
diagnostic tools. In fact, the one of other we're using in this paper, that's really the main thing, the spectrum form factor, that
Hmm.
now people been looking at. Um, but yeah, so that's really the idea indeed. So let me also mention that, initially, like in those, like in 1950s, 80s, people were starting from, I guess, like the classical models and they were quantizing those classical models. So now
Hmm.
actually we're not really doing that kind of like, quantization process to classical models. Rather, we are starting from quantum many-body systems and they don't have necessarily a classical analog to them. um
Hmm.
it doesn't go like that, just because you have a quantum mechanical model doesn't mean that you're going to have a classical analog for it.
Right. Yeah, that's
Hmm.
understood.
Yeah.
Good. I want to get to the spectral form factor as well. Maybe
Yes.
first we could touch upon stroboscopically driven cold atoms, those kind of systems in particular, and what they mean. Would you mind introducing those?
Yes. Okay, so cold atoms are like literally like an ensemble of atoms that are like trapped and cooled down to like the nanokelvin temperatures. So
Hmm.
that's why they're pretty cold atoms. And when we do this kind of process, basically like they become more controllable. And it is like the field of cold atoms is actually one of the let's say hardware for quantum science and engineering applications today. Um,
Hmm.
so one could typically the cold atoms is a very good platform for quantum simulation, but today like with some alternative like systems, they're also a very good alternative for a quantum computer too, with like particularly tweezer arrays. But in this particular case we don't
Hmm.
think about like the Rydberg atoms and tweezer arrays. We're thinking about cold atoms trapped in optical lattices. um you can just as an analogy we can think of a solid, like so there this in the solid like the you have electrons moving around and you have your atoms, right? For your crystal structure that creates some sort of potential wells for your electrons. So basically that is like really the analogy that we have for the cold atoms in optical lattices. We have these atoms are like loaded into like the lattices, but lattices made out of like light. For example, like you can shoot two laser lights from two directions. It's going to create a standing wave, and if you can make like light matter interaction between your atomic species and like your light, then you can actually really trap them in the minima of these like optical lattices. And that's going to be a
Mhm.
really nice, like, model to study like the physics that we see in the solids, for example.
Mhm.
Those are the cold atom models that we're studying here. For example, Bose-Hubbard model that we study is a model for bosonic quantum particles in the optical lattices. And then the second model that we look at is a spin half Bose-Hubbard model, which means like this particle that you trap in the optical lattice has a spin degree of freedom, up or down. Could have that kind of
Mhm.
extra degree of freedom to it. The third one is actually the non-integrable spin-1 condensate is different. There is no lattice in this particular case. It's just a gas of quantum mechanical atoms, let's say. That means like there is no spatial structure to them. So they're all together like a gas, but they're still quantum mechanical, this entire gas. So that we write down like a quantum mechanical Hamiltonian for it and study it. So these are the models that we're studying here.
Mhm. Maybe we can go to the operator down here as well that you're using to drive this with. Could you briefly explain what we're trying to do with this operator? Like, what are
Yes.
we? Yeah, how are we affecting these atoms?
Right. So that's the definition of stroboscopically driving part, which I was just coming to. So these are okay. These are the systems that I just talked about. Like one could write down just a Hamiltonian for them. It's going to be a time independent Hamiltonian. But what we are trying to do here is we're driving the system, like you said, and it's not a continuous driving. For example, it's not like a cosine. Let's say a laser, like it's not a laser driven, let's say, in that sense, like it's not a cosine or a sine term, not a like sinusoidal term. Rather, like we
Mhm.
are thinking about driving the like first evolving the system with one type of Hamiltonian, and then the second step with another type of Hamiltonian, for example in this two-step protocol, and then we just repeat this over and over again. And that creates actually a periodic driving, but stroboscopically driving.
Mhm. Okay. And then the three step, how does that differ? It's just that we have three different cycles, or
Exactly. So it's just like you can see that there are three different steps to it, and then it repeats again. So what this creates, a U operator is a Floquet operator that we call,
Mhm.
and because this entire formalism is based on the Floquet engineering, Floquet periodic driving, and the Floquet theorem. And what three-step does here is it breaks the time versus symmetry and then creates this other types of random matrix theory distributions to come in. In the beginning of this like chat, I had mentioned, like you can have orthogonal ensemble, you can have unitary ensemble. That depends on whether you actually preserve time versus symmetry or not.
Mhm. Okay. Also, I think related to the different models that we're considering is, I believe it's figure 2, if I can find that, up here. Um,
Yes.
could you give an overview of what this represents? And
Mm-hmm.
yeah.
These are basically the schematics of the models that we're studying. So spin half, as I said, like in a bit before, it's like you have like bosonic species subject to this optical lattice, but it has like spin half spin degree of freedom, so either up or down. So this is basically how you can realize in a cold atom platform this kind of like system. You can actually like, because each atom like comes with like a hyperfine level structure, and that means basically it has like energy levels that if you have the right laser like frequency, you can actually couple these like different energy levels. So we can imagine if you wanted to make like a spin half like Bose-Hubbard model, then we can encode like spin one and spin up and down basically on these hyperfine levels. So this is actually what this picture corresponds to. The one of the optical lattices here, the lattice like it corresponds to having the atoms in this like one of the hyperfine levels that is denoted by the spin up, and then the other one is with the spin down.
Mhm.
And then the second one, B here, is the spin one condensate. As I said before, there is no spatial structure. It's just all these atoms are confined within like this harmonic trap. I mean, they have to be always in this harmonic trap because you're trying to trap these atoms and cool them down. Um, and um, and this is basically what the schematic shows you. It's a gas of atoms.
Okay, and the solid lines on both of these figures represent energy potentials that are keeping these atoms in
That's right.
place. Then I suppose. Yeah.
Exactly.
Okay. Okay, very good. So then maybe we can have a look at this figure right here, because I think there's quite a lot to say about that one, or I think it's a good introduction. So could you introduce the spectral form factor, and then we can talk a little bit about what we see in the figure?
Right. Okay, so the spectrum form factor is actually another diagnostic for quantum chaos. It also comes from random matrix theory. It has more information than like, energy level distributions or like energy spacing distributions. So in C, actually in figure 1C here, you see like, this the red line here is what I kept saying here, like Wigner-Dyson distribution. That is a distribution that is again coming from RMT, random matrix theory, and that tells us the distribution of the smallest energy spacings. So if you have your energy spectrum, right, you can just calculate the energy spacing between all of these energy levels. And when you plot this, that's going to give you a histogram, a distribution. That's exactly what the C is doing. And this is like specifically like to the detail. This is what random matrix theory, predicts. It's a specific prediction for the energy levels. So now when we come to when we come to spectrum form factor, it has more information. It is literally like the Fourier transform of two-level energy correlations. So if you think about what's a two-level energy correlation, it is literally this. What is the probability of having an energy at E1, let's say, one energy level, given that there is an energy at, let's say, E2? So this is what that energy correlation function is. And spectrum form factor is the Fourier transform of it. So because it's a Fourier transform, it takes energy domain to a time domain. In the end, what it gives you like a time dependent, an observable. And we like that kind of thing because today, like in the era of quantum technologies and the quantum simulators, that's something that we can probe. We do have like real time dynamics that we can probe. We can get data for. So that means we can potentially like measure this thing too, because it's a time evolution basically. Okay, so let me also very quickly mention what these like curves stand for in the spectrum form factor. So in the spectrum form factor, like there is like two main features. It's what we call ramp and the plateau. So the time scale that connects the ramp to the plateau is called Heisenberg time. And that is actually the time scale that you can resolve like the most. So this like a long times corresponds to the shortest energy distances. So the smallest energy levels that you can resolve. And that time scale basically also corresponds to this like nearest neighbor, like the smallest energy distances, and the distributions for it. That's why there's this like the green like arrow here, because that like Wigner-Dyson distribution that we were checking is actually really referring to this Heisenberg time scale. And then the plateau is basically like saturates exactly at like 1 over the Hilbert space dimension. So it is like if you're actually working with a larger system size, your Hilbert space dimension is going to increase. So you can see that this is going to basically it's going to increase. So this is going to be actually smaller and smaller, this plateau value. And then like the ramp is what it's telling you is like you're going basically like smaller in time. And that is also a universal feature. it's really coming from the random matrix theory. When you do the like a calculation for the random matrices, you do actually expect this kind of ramp behavior here. And what it's telling you is there are correlations beyond like the shortest energy distances. There are correlations actually in the long energy distances as well. Literally, this is like the gist of this ramp.
Mm-hmm. Okay. And those correlations then attenuate linearly as the distance increases. Is that also what this graph is telling us, or am I reading it wrong?
Um, what it's no, it's actually, it doesn't say anything about the strength of the correlations. It just tells us that the presence of the correlations. So we have a connection through like, like an uncertainty principle. We have the energy time connection. So smallest energies means like you're looking at like large times. So
Mm-hmm.
if you're looking at small times, that also means that you're like looking at large energy distances, let's say in the spectrum, in the energy spectrum. So the fact that I'm able to see this ramp appearing in my quantum mechanical system tells me that there are like, the correlations between energy levels that are pretty distant apart from each other. That's just what it tells us. And then also on top of
Mm-hmm.
it, like denoted by stars here, that's the time that we don't see the ramp behavior anymore. There is a divergence from that ramp behavior. So
Mm-hmm.
that time scale is what we call onset of random matrix theory. Um, and that means like, there is basically the random matrix theory stops like working. It doesn't give us any more like predictions for even like the shortest times. But this is exactly what this paper is looking at, actually, whether there could be some sort of universality in this very short times.
Mm-hmm. Okay. And then we're talking about this refers to the bump as well, right? That's what we're referring to with
Yes,
this part of the figure right here. Now,
exactly. Bump region.
would you mind giving some conceptual understanding for why we have a bump there? What does that represent, if we can say anything about that?
Yeah, so this is actually still an active research, what this regime really stands for. But we do have like some sort of intuitive way of thinking about it. Um, so typically we see this bump region in like locally connected systems. So what I mean by that, for example, is like these atoms in optical lattices, right? So um, they are basically like there is some sort of local structure, a spatially local structure to this model. Um, that means not like, when we look at the system, too far apart regions of the system don't know each other like, right
Mm-hmm.
away. What we also call like, the system shows like certain linear, like certain light cone structures in time, like these different like far apart regions of the let's say a chain or like, a system. We'll start like seeing each other in time, basically, because they are like, confined within some sort of information light cone. um,
Mm-hmm.
and this happens because, initially the system like doesn't know that it's chaotic, and it starts to just like increase like rapidly, like, because that's what we expect. If the system is not chaotic, uh, the spectrum form factor should exponentially increase to the ramp behavior. So you can see, for example, this pink line here in the A. This is a Poisson case that we are saying. That means like if you don't have a chaotic system, you should just immediately see like this plateau behavior. You shouldn't see the ramp behavior. So that's what this, the way that we think about this bump. Okay, system is not seeing it's chaotic. It's very like, short distances and tries to like, exponentially increase. But there is a certain time that it realizes that it is actually chaotic, and tries to go back and approach to the ramp, basically, and then have this onset of random matrix theory coming in. So this is
Mm-hmm.
why, like, there's this kind of structure, bumpy structure there.
Mm-hmm. Okay. How come you need to have everything like the entire system encompassed in the same information light cone before the system actually knows that it would become chaotic, if you understand or if that question makes sense.
Um, so it doesn't make sense completely, but maybe what I can say is because like let's think like this: if we have one chain, right, and then let's
Mm-hmm.
say like each side is just coupled to its nearest neighbor sides, and it's not coupled to the next one. So that
Mm-hmm.
means initially like this side is just gonna know about its neighbors. That's it.
Yeah.
But then
Mm-hmm.
in the next time, like is the system evolves, it's gonna start getting correlated with the next nearest neighbor, and then and the next nearest neighbor, and that's exactly like the reason why you would have like a light cone in the system. So that's what I mean when
Yes.
I say it's locally connected, and it has like the information has a speed to it basically. So two far away sides of this chain is not going to be correlated right away. There will be some build up time for these sites to see each other or correlated, or like in more mathematical level, when you look at their commutator, it's going to start being non-zero basically.
Mm-hmm. Yeah, that's understood. And my question then is, as a follow up to this, if we have a
Mm-hmm.
system where we have correlation after some time period with the different parts of the system, if it is a chain or whatever it is,
Mm-hmm.
it seems like the system during very early time periods behaves as if it's not chaotic, and then
Yes.
if I understood your previous explanation correctly, then realizes after some information is passed, after this light cone has gotten large enough, if you will, that it's actually a chaotic system. My question is, why is it necessary to for the information light cone to expand before the system actually realizes that it's chaotic? Is it a feature of all these systems that that if you consider just a subpart of the system, it would not be chaotic?
Mm, it is. So um it is a feature of all these systems that are having this like local structure to them. The So basically, yeah, it takes time for this like how to say this, like information is indeed like has a speed to it, like to spread in this like system. So it
Mm-hmm.
is like clearly what we see here as well, like it's clearly affecting like the energy level structure too. So um maybe, I mean, if it explains more, but I am actually having a hard time like really understanding your question. So
Mm-hmm.
maybe
Let me see
maybe
if I
you
can
can,
formalize it in a
yeah, that would be useful.
because the point about the information spreading and taking some time to spread through the system is perfectly agreed. Like that to me is not hard to get my head around. What is hard to get my head around is that um, the information spreading is a necessity for the system to become chaotic. So it seems like
Uh-huh.
the system does not behave
Yes,
chaotic until there's a correlation built up between distant parts of the system. My question relates to that.
exactly.
That it seems like the system doesn't
Exactly.
become chaotic until the correlation is built up across big parts. And my question is why? Like if you have a smaller subpart of the system, why does not that not also become chaotic? Is it a feature of all of these that you need to have correlation between different far distant parts of them for them to turn chaotic?
Yeah, okay. I see much better now what you're asking. Um Indeed, like, so okay, let me say it like this. Um we do think that there is actually a connection between the information scrambling, or like the information spreading, and the many-body quantum chaos. But this is like the whether like how the connections are really made, it's still actually like something that people have been trying to figure out. And that's because when we say quantum chaos, as I like defined or like defined in the beginning of this like chat, um it's really a statement about the energy levels and actually the energy eigenstates. um when we talk about information spreading, that is typically a statement also about like the observables. So basically in that kind of like, you know, setting, you have like local observables that you look how they actually like how they actually get correlated with each other. So the connection between these concepts are actually still being like how to say being developed.
Mhm.
So it's actually not immediately clear. So this picture that I gave you, like, you know, it's really just like the rough intuition. Um, so what we are seeing in the data. So I
Mhm.
can't really like tell you like, you know, how like, you know, the very like solidly these concepts are connected to each other, because like it's still like, you know, we are still like trying to understand that ourselves.
Mhm. Understood. And this figure that we're looking at is generated by a chain of atoms, or what is it
Yes,
that is okay? So
it
a
is.
follow-up
Yeah.
question then would be, if we have a chain, I don't know how large this is, but let's say we have, I don't know, 50 particles in this chain. If we reduce the amount of particles, does there come a point where it stops being chaotic?
Um, so there, even for very small system sizes, you will still see this kind of ramp and plateau behavior.
Okay.
Um, like say like it's not, yeah, indeed. I mean, there is actually we do have like an experimental now observe we experimental actually observe the spectrum form factor. And even for small system sizes, like you know, let's say like 3 sites, you will still see this ramp plateau behavior. So even for them, like it will be there, but whether like you can see this kind of like the onset of the random matrix theory and the bump behavior, that's a different question. It's typically very hard to see those ones like in very small system sizes.
Uh-huh. Because if I understood your explanation of this one correctly with the bump here, I would expect it to disappear if the system becomes small enough,
Yes, it
because
does.
that would essentially be equivalent to not having the information propagated all the way
Right.
in a larger system.
Right. It's actually really hard to see this kind of feature. It kind of like, you know, flattens out and goes away. Let's say for 3, 4 system, the system size at like 3, 4 sides.
Uh-huh.
Yeah.
Okay. Okay, understood. But then let's focus on what you actually investigated a bit more in the paper. So you're focused on the bump that we're seeing here in well, on the left hand side of this graph. What is it specifically that you investigated then? And then maybe we can switch to some results.
Yeah, okay. So really like it's actually very simple, the topic of this paper. Um we wanted to see whether there could be any universality to this region. So whether there could be any universality in the many-body quantum chaos beyond random matrix theory. To see that, like, you know, we have this multitude of models. They're microscopically different models, and we also different driving mechanisms like 2-step, 3-step we just mentioned. So that means like, you know, we might be taking time versus symmetry into account or not. Um, and if, like this kind of further details. Regardless of any of these, we see that like all these models show this bump region in one way or another. And a nice way of showing, like, you know, whether there is a universality or not is rescaling like the yeah, for example in this plot here, like rescaling the x and y axes and see whether these, like, you know, data for different system sizes collapse on each other. um that's just like a typical way of, like a standard way of checking whether there could be universality in the data that we're seeing. So um the for that particular one, it's I think figure 5, it should be figure 5 or 6. We basically rescale the not this one but the one later, yeah, 6 I think.
Okay.
Yeah, we rescale the time. Yeah, here. Like time with the talus time, and the talus time here is the onset of random matrix theory. That's like the onset time that I was just mentioning. And then the y-axis, the spectrum form factor with the analytical prediction that is coming from the random matrix theory. And we see when we do these rescalings, already the data for different system sizes collapse on each other, and that suggests basically like there is a universal the approach to this ramp. in this bump region. And all of these, like these different subfigures belong to different models, basically. All of these basically suggest like this behavior is power law, regardless of all those microscopic details. And in general, this might suggest that there is indeed some like universality beyond the random matrix theory when we talk about like quantum chaos and quantum chaotic models.
Just for me to understand also how we generate these figures. So we perform the Fourier transform as we discussed before, and then we end up in the time domain, and then we want to evaluate this over some large interval. How do we actually get data points for this? So we have a time dimension now, and what does that time dimension actually represent?
Yeah, so the really where we are starting is we're starting from the spectrum form factor in a time domain already. So we're not actually like, Fourier transforming. What we are doing to get the spectrum form factor, we have those like, Floquet unitaries that we were just looking at, right? So if we go to like one of the equations up there, that is, so I can show actually. It's one of the first equations. So maybe equation 1 even, because that's the spectrum form factor. Yeah, okay, equation 1, exactly. So this is how the spectrum form factor is written in time domain. So you have your unitary in between. So you take basically the trace of it and then absolute value square. This brackets outside, those are basically averaging over many statistically similar systems. So this spectrum form factor is not self-averaging, meaning like, you have to actually calculate it as an average of many different systems. So this is how it's defined. Yeah. And then the U of t there is the, evolution operator. You write it down based on the Floquet unitaries.
And that's the one we looked at in the beginning, I suppose.
Yes.
Or is it different from the equation that we looked at first? I think it's right next to, yeah, it's here.
Yeah, so this is like the, Floquet unitary for a cycle. U of t in the spectrum form factor is going to be this, and then this one multiply like say n times to generate the entire time evolution, because it's a periodically driven system.
Okay. Very good. So we found some commonality then in these graphs, and I think there's a power law that describes these in some way. Could you elaborate a little bit on what that result was for the paper?
You mean the importance of this result for the paper?
Yeah, I think you in the end resulted in a function depending on two quantities. I think it was the system size and then something else as well.
Oh, I see what you mean. Yes. So right. So there's this additional factor here, like so in the Bose-Hubbard model, we have two main factors that affect the Hilbert space, the dimension of the Hilbert space. One is the system size, like the number of sites in your chain, and the other one is the number of atoms that you can load into this chain. And for example, the ratio of these define the filling factor of your lattice. So let's say, you have 10 atoms in a 10 site system. That's going to give you a unit filling, we would say. So we looked at basically the differences, whether there could be any difference in the spectrum form factor, in the spectrum form factor between like these two factors, like, and we found like bump regime is more enhanced when we are actually looking at the when we're looking at the cases where we have more atoms than like the number of sites, compared to the other case where like we might have like smaller number of atoms, but like, trapped in larger chains. This is basically one like result that came out from this data.
Do you have some conceptual hypothesis for why that might be?
We were thinking that this could be related to the fact that this could be related to the effect of interactions, because these are like strongly correlated interacting many-body systems. So when you have more atoms, that means the you're basically increasing the that kind of correlation that is coming from the interactions between your atoms. So if you're, say, like loading just three atoms in like a very large system, um, they can actually like organize themselves far apart from each other, and that could decrease the overall interactions in your system. So we were thinking there could be this kind of like an effect of the interactions that we're seeing as the enhancements of the bump. But again, these are like just let's say some like ideas coming from like this data. I think there needs to be even like more like research here to really understand like what this bump regime is like probing, and also on top of it, like whether there could be any other observables that has the effect of this bump regime.
Mhm. Okay. Maybe that ties it nicely into upcoming research because we only have a few minutes left. But you mentioned that we could study the bump regime a bit more. Are there also other systems that we would like to study? So we have a few systems that were investigated in this paper. I don't know if there are other ones that are of interest to us from an academical point of view that perhaps, well, that perhaps don't even have this bump regime to begin with. Or do we always observe this? Do you know in the rest of the literature whether we see a similar story for other kinds of systems as well?
Yeah, so this is a very interesting question. So indeed, actually, this the even like a possibility of this like a regime where we could have universality beyond random matrix theory came actually from random circuits. So there is this like there is a very huge interest in like random circuits, and particularly the local random circuits. One of these like models, let's say, in this kind of system is the brick wall model, which immediately gives you like some linear light cone. So it's a locally connected random circuit. When I say random circuit, maybe I mean I can also explain like you have your gates, like 2-qubit gates in your circuit, and those like the 2-qubit gates are sampled from like a Gaussian distribution, let's say.
Mhm.
So the first like signature of these bump regime actually was seen in these random quantum circuits, and then like we wanted to see whether they also this regime also appears in like more like physically realistic systems. um there are some like papers here and there that if you like look, like you might actually see some signatures of this, but basically overlooked. So typically, we would expect this kind of regime to appear um, if you have a chaotic quantum many-body system with some local structure. Um, Even I would say like it doesn't have to be like a very local, like it doesn't have to be nearest neighbor, let's say. There could be like even like a little bit like long range nature to it, but still like the it's still like the it might actually more depend on like um how the light cone looks like. So based
Mhm.
on this, there could be actually a platitude of a plethora, sorry, a plethora of like models um, that should actually show this behavior. Really, the one thing that one needs to um, take care here is that we're working with this driven, like periodically driven system, and the reason why we're working with the periodically driven is because it nicely shows up this bump region, and that is related to the fact that in a periodically driven system, when you look at the density of states, you're gonna see like a flat distribution in the density of states. So that complete takes out like what we call like the edge effects, spectrum edge effects. Um, if you have a time independent Hamiltonian, you're gonna have these like edge effects there. And typically that brings like a non-universal part to the spectrum form factor. And that could like overshadow basically this region. It's already very small there for the system sizes that we have. Um, and that could be like a problem, like we might not be able to see it there basically, or one needs to like subtract that non-universal part from the spectrum form factor to be able to see this kind of thing. So I think that's really one thing that one needs to take care. But other than that, exactly what we expect from the universality of this regime, it should be there, I think, for many
Mm-hmm.
systems.
Mm-hmm. That's interesting. Any other, well, future points of research that you think would be important to highlight beyond what we mentioned in the paper? Because I think we're at the verge of closing after that.
I think a very interesting thing for me is I like to see whether there could be what is like the direct effect of this bump regime on the information properties. So what chaos in the end means is like that your system becomes featureless. Okay, so we know that at the onset of random matrix theory, your system becomes featureless. So if you started with some entangled state initially, and you look at this time scale, that entanglement should at that point, completely scrambled into the rest of the system. So basically, you shouldn't be capturing anymore like any like local information, let's say. So what I'm
Mm-hmm.
curious about, like now we're seeing this kind of like some sort of hint of universality beyond random matrix theory, and in this early times, what is the effect of this to like say like an entanglement structure of an entangled state? Um, is it actually gonna like corrupt it like earlier, or like or is it does what kind of effect it's gonna have? So I think that's an interesting question that that I might actually work at some point.
Mm-hmm. Awesome. Very good. Then I think we'll actually wrap it up here. I really enjoyed the discussion, so thank you very much for taking the time. It's been
Thanks so
great.
much.